Next video, boundary conditions. Let's do the thing. All right. Now, I'm not actually talking about setting boundaries in real life, although that's very important also. It was just a clever title. But yeah, work-life balance, I mean, it's a thing. You can, in fact, make it happen if you make it happen. It won't happen for you, but you can bring that about if you put in the work to do so. But the boundaries we're talking about here are system boundaries, the boundary between you and the rest of the universe, or whatever the system is that you're studying. So let's get into it. I'll just jump right into this is a big deal because this is what determines the difference between good answers and bad answers. It's that simple. Good handling of boundary conditions leads to better solutions. Bad handling of boundary conditions can lead to anything from solutions that are literally impossible, like your code just won't run, it won't converge, it won't get a solution, or even worse, it will give you a solution that's just crap. It's like, my boundary conditions do not reflect the reality of the situation, and they're so different from the reality that my answers are as a result. Now, this is part of the art, the skill, the craft of numerical methods, is defining good boundary conditions, because you might know the exact physical boundary conditions of your real situation that you're trying to model. Great. But just because you know them doesn't mean it's reasonable to put them into the computer exactly as they are. The computational cost of working on those might simply be too great. So instead, you might have to make simplifications, make the boundary conditions, and then this is the skill, make them simple enough that they compute reasonably well, but make them true enough, high enough fidelity relative to the physical situation that you're modeling that they are still useful. We're after useful answers here. They're not going to be perfect. They're not going to be infinitely accurate, but they need to be good enough. And a mistake that I see students make all the time when they're trying to do modeling work is they try to do everything exactly and do everything exactly correctly. And then they're like, my code won't run. No, your code's running. It'll be running for the next 30 years. Go have a beer or, a non-alcoholic drink or whatever. But you have to make some compromises somewhere. There's always this tension between computational pain and accuracy of solutions, and you have to navigate that trade-off. Okay, so setting good boundary conditions is part of that. That was the philosophy. Now I'm just going to talk about practical details and try to keep this relatively short, like 10, 12 minutes, hopefully. The first kind of boundary condition I want to introduce is the Dirichlet boundary condition. So we're trying to find some function that changes over time. This is the story of the whole differential equations business. And you might know the value of that function at the boundary. You just don't know it inside the system. So let me go back to my auto body panel example. You're like, I want to do a heat treatment on this aluminum body panel to increase its strength. Seems reasonable. Well, in this case, you're going to take that body panel and put it into a heat treatment oven, and you know that the oven is at a fixed temperature. So you're going to have this known temperature versus time function all around the body, all around the boundary of that body panel. That's what a Dirichlet boundary condition is. You know the value of the function outside, you're trying to find the value of the function inside. You're trying to answer the question, what is the temperature versus time everywhere inside the body panel so I can know when it's reached the correct temperature for the heat treatment and grown whatever precipitates it needs for precipitation strengthening, blah, 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 material science. So this is the Dirichlet boundary condition. The value of the function at the boundary is known, and we go from there. That's one of the two most common types of boundary conditions. There's a bunch, but there's really two super big ones that you gotta learn first. Dirichlet is one, the other is the Neumann boundary condition. This is the same situation. We're trying to find how our function changes over time, but we don't know the value of the function at the boundary. And before you throw up your hands and you're like, this is impossible, I quit. No, it's okay. really, it's okay. Because we know the derivative of the function. You're like, what? What? How can I know the derivative of the function without knowing the function itself? Well, let me talk about my example here. How well planned. Good job, Tim. Thank you, Tim. Yeah, you're right, Tim. Okay, sorry. Um, when might you know the derivative without knowing the value? Reaction problems are a great example of this. Imagine we have some reaction chamber. We're going to feed two different gases into it to cause a chemical reaction to happen. Uh, I'm not up on my gas chemistry. I'm just going to pick methane and oxygen because they came to mind. And we have these regulators on our intake lines. So the regulator will allow some flow rate of methane into the system, some number of moles per second, molecules per second, whatever. That's DFDT. We know the rate at which the function is changing at the boundary, even though we might not know the value of the function itself. And this is not at all crazy from a differential equations point of view. It's very reasonable to talk about how something is changing without saying where it is. So, Dirichlet boundary condition, we know the value of the function. Neumann boundary condition, we know the derivative of the function. Most cases that you'll encounter, especially early on, are one of these two things. There's other kinds of boundary conditions. They're a little bit more complicated, and you deal with them in a different class. Now, those are the categories, but how do we implement these in the code? Because last time I was showing like, here's your data array, here's how you structure the data, and you put values in an array and you calculate things, yada, yada. Well, what happens at the edge? How do you actually implement the boundary condition in your code? Well, when you're doing numerical derivatives, you have to think about these things because you're not solving an infinitely tiny window, some limit as epsilon goes to 0 of whatever. You're doing slopes over finite intervals. And if your derivative is, so like I have a right derivative written here, well, you have the function on the right minus the function on the left divided by the interval, because that's your rise over run. What if there is no function on the right? If you're on the right wall of the system, where do you go from there? You can't take the nothing and then subtract the something from it because it's not even 0. It's nothing. It does not exist. It's not a number. So how do you handle this? Well, you could throw up your hands and cry and quit and flip the table and whatever. You could do something really dumb like I did and come up with a clever picture to amuse your students and be like, yeah, this is what happens at the edge of the ice wall that's surrounding the flat disk that is our Earth. I'm sure I'm on some kind of flat earther email list as a result of searching for this. So you're welcome. I hope you're amused. But no, your numerical solver can't just fall off the waterfall at the edge of the world. It has to do something. And giving up is not an option. We're going to win. So one thing you can do is you can actually extend your system. You can say, I am going to make a bigger grid than I need, and I'm going to solve the grid, but I'm going to do my derivatives just in the inner region away from the edge of the system. Yes, this introduces inaccuracies, but if you're only interested in the inside part, then the inside part might still give good answers. So you can do that. You can create extra space outside of your system and put values into those spaces so that you're able to do derivatives. Another option, I forgot to make a slide for this, is you can make choices between how you calculate the derivatives. I mentioned in the last video with Hoyne's method for doing corrections that there's left derivatives and right derivatives. There's also the symmetric derivative, and okay, we could go places. But if you're like, well, I'm at my right edge of the system, so I don't have a value to the right, well, I'll just use the value to the left. I'll calculate a left derivative on the right boundary, and so that works fine. And I'll calculate a right derivative on the left boundary, and that works fine. So you can do that as well. It'll take a little bit of extra logic or checking in your code as you're looping over stuff to make sure that you're working with values that exist, but you can do that. So you can extend the system. You can use different derivative calculations at different boundaries, or you can go big brain. I should have put like the galaxy brain meme here. You can use periodic boundary conditions. This is the way. I think there's a TV show about that. So sometimes your system is truly periodic. And in that case, this is a no-brainer. Like if you're working on a crystalline structure and there's some lattice, there's some lattice that's periodic and symmetrical and all these wonderful things, then use periodic boundary conditions. Your system is periodic. You expect your solutions to be periodic. Make your boundary conditions periodic. Everyone wins. Hooray. And we can do that often in material science because we study a lot of periodic systems. But sometimes your system physically is not truly periodic. Then what do you do? Well, you can actually get away with this. What you do is, implementation wise, you're like, okay, here's my system, here's my box, great. And I'm at this point in my grid and I need to take a derivative. Well, there's no derivative to the right, but what you can do is you can just grab the value from the other side of the box. And you're like, this is cheating. I hate it. I resent it. Look, back in my day, we had two-dimensional video games where a round world was represented by a square box. And when you walked off the right side of the box, you appeared on the left side of the box. And we liked it because that's how we thought about our worlds being round. So there, darn kids, you don't know how good you have it. Okay, putting that aside for a second. If your system is periodic, this is totally fine. Any one point is as good as the next because you have some kind of translational symmetry. But even if your system isn't periodic, you can still justify this, or at least you can get away with it, which is just as good or better. Because your system, if it is large, this is essentially the constraint. If it's mostly volume and only a little bit of edge, if your edges are very slightly wrong, because instead of grabbing the like true value at the edge, you're just grabbing the neighbor from the other side of the data array, that's going to give you slightly wrong answers at the very edges of the system, but most of it's going to be totally fine. So again, you can often get away with using periodic boundary conditions, even for a non-periodic system, as long as you have a large amount of inside relative to how many boundary points you have. How much is enough depends how accurate your answer needs to be. And edge effects are a thing that we deal with not just in numerical methods, but actually lots of places in the physical world. If we're talking about a capacitor, for example, yes, physics 240, grab your torches and pitchforks. I can hear you booing already. Whatever, I don't care. You got to get good. So you're dealing in capacitor. Capacitors are filled with materials, by the way, dielectric materials. It's all about the polarizability of the atoms. Very interesting stuff, but I digress. In the middle of the capacitor, if you look at any given electron, it's surrounded by a whole bunch of electrons. The system looks symmetric in all directions. And so you have a very nice regular electric field, storing that electrical energy. But near the edge of the capacitor, the electrons in the edge look in one direction, they see all their buddies, they look in the other direction, they see nothing. They scream into the empty void, wonder about the nature of existence. Is this, okay, maybe they don't, they're just electrons. But you will get an electric field that's shaped differently at that edge because the edge of the system does not behave like the inside. That's just how it is. But that doesn't mean that all of our capacitor equations are terrible. It just means that they're approximations. And as long as, I know I said this before, but I'm saying again because it's important, as long as the amount of edge of your system relative to the amount of middle is a small ratio, your answers are going to be accurate enough to be useful. An example in materials characterization is when we're doing X-ray diffraction. Crystals, surprise, I hate to break it to you, but crystals in the real world are not infinitely large. And when we calculate those beautiful, perfect diffraction patterns, we imagine that there's these infinite numbers of planes of infinitely, did I say that wrong? Infinite number of infinitely wide planes of atoms that are creating these perfect, infinitely symmetric, periodic, translationally invariant diffraction patterns. And that's a great approximation as long as your crystals are pretty big. Because the way X-rays scatter off the edge are different than the ways that X-rays scatter off those repeating planes of atoms. They're different physical situations. But if most of your signal is coming from inside the crystal and only a little bit comes from the edge scattering, it's still going to be pretty close to the ideal result. And if you want to learn more about that, take the lab classes, we'll talk about it. So, where does this leave us? We have Dirichlet boundary conditions, we have Neumann boundary conditions, and you have a few different options for how to deal with the boundary when you're calculating stuff at the edge of your system. This is where it leads us to the homework. How did I do on time? Terrible. I talked so long. All right, we got to wrap this up. The homework this week is a little bit different from the usual. It's not just going to be a document with questions. It actually is a Python notebook that you will work your way through. So this is something that Mia and I have been building over the last couple weeks, and I think it's going to be pretty good, actually. I expect it to work. Is that a weird thing to say out loud? I hope I didn't just bring misfortune upon myself. Last year, there were some struggles with this topic, and part of it, to be, of course, completely honest, is it was my first time teaching the topic, not my first time doing this stuff, but my first time teaching it. The first time you do something, it usually doesn't turn out that great. That's just the reality of being a human in the world. So there certainly are things that I realize now, oh, I should have taught that differently. So you are getting version 2 of the instructional approach. I hope it's helping. The other thing, though, is last year the homework was just structured the same as the others. Here's your problem, do this stuff, here's some hints, go. And this time we wanted to structure it a little bit more intentionally and have more of a building sequence of working your way up through more complicated situations and developing your code base with some structure as you go. So I do actually optimistically expect this to go better than last year, but if nothing else, we can always go with, all right, go be better than those students, prove how awesome you are. Anyway, yeah, we'll post that Python notebook for the homework for this week, and that will be what you'll work through, and then you'll submit a document with your responses and your output as you usually do. All right. If you have questions, I should probably just say when you have questions. This is one of the harder assignments. It's entirely numerical. You have some experience with doing numerical work now. You've used different code creation processes, looking stuff up, using AI assistants, large language models, you name it. Great. So let's put that to the test and do some work and solve some partial differential equations. When you do find yourself getting stuck, come ask for help. That's why we're here. We want to help you succeed. It's not a secret, and it is a game in a sense, but we're all in the game together, so let's win it together. All right, that's enough of that. I will see you next time.